In this video, we're going to talk about how to find the magnetic field at the center of a partial loop of wire. So our black line, the black curved line at the top, is some loop of wire, which doesn't create a full loop, it's just a partial loop. If we continued this line around, it would make up a full circle, but we only physically have part of a loop. To find the magnetic field at the center, we can use the equation B, the magnitude of the magnetic field, B is equal to mu naught I delta theta over 4 pi r, where r is the radius of the loop here, and delta theta is the angle subtended by this partial length of wire. In this case, we can find delta theta by noting that 180 degrees must equal 25 degrees plus 60 degrees plus delta theta, which leads us to delta theta equals 95 degrees. Now, in order to use our equation here for delta theta, we cannot have our delta theta in degrees. We need to have delta theta in radians. So what we're going to do is we are going to convert our 95 degrees into radians. And to do that, we simply use our conversion factor. So we take 95 degrees, multiply it by pi radians divided by 180 degrees, which is going to be 1.658 radians. We do this because radians are a fundamental unit that tell us about distance around a circle. So for example, the circumference of a circle is equal to 2 pi r, 2 pi times the radius of the circle. You can't find the circumference of a circle by saying 360 degrees times r. So radians and this idea of pi is much more fundamental than the idea of degrees and 360 degrees. So we, in this case, have to use radians in order to find our magnetic field. So now what we need to do is find the direction of the magnetic field at the center, and we will be able to find the total magnetic field there, because we know the magnitude from our equation, and if we have the direction, then we have the entire magnetic field. And we can do this by using our right-hand rule. So if we remember the Biot-Savart equation, so that is dB equals mu naught I over 4 pi times dl cross r hat over r squared. And the thing that we care about in this equation is this dl vector cross r hat component, because this is going to tell us the direction of our magnetic field. It points in the direction created by this cross product of these two vectors. Some point along the wire, and we can draw this dl vector, which points in the direction of the current flow at the point that we chose. Now, the point that I chose is completely arbitrary here. This direction that we find is going to be completely independent of which point we choose to do dl at. That is, we could choose another point over here, and we'd find the exact same answer for the direction. Okay, so dl here points up and to the left, and then my r hat vector points from this point towards the center. So this is my r hat vector. And if we take this cross product, we can just use the right-hand rule for this. So our index finger points in the direction of dl. Our other fingers point in the direction of r hat, which means that our magnetic field at the center must point out of the page, because when we arrange our hand this way, our thumb points up out of the page. So the magnetic field at point P points out of the page, which is our k hat direction, assuming that we have a positive x, positive y coordinate system here. So we can write the magnetic field at the center as being mu naught I times 1.658 radians divided by 4 pi r in the positive k hat direction. So given some I and some r, you would be able to actually write down a number for this magnetic field and know its direction.